Let's have a look at this limit. As n approaches infinity, we have 1 plus 1 over n times 1 plus 2 over n times all the way up to 1 plus n over n, and the whole thing raised to the power of 1 over n. So what's going on with this limit is that, so as n approaches infinity, we have the first term approaching 1, second term also approaching 1. But the problem is that the last term is actually equal to 2. Right? Perhaps the previous term also approached 2. So that, and also we have infinitely many terms in here, so it's still undetermined. So what we're going to do is that first we're going to take logarithm. Right? So every time we see that there is a power, then we take log. So after I take logarithm, I just take down the power. And I have log of this whole thing. A log of some product can be written as the sum of logarithms. I have log of 1 plus 1 over n plus log of 1 plus 2 over n plus all the way up to log of 1 plus n over n. Bracket. Now, that is essentially the very definition. If we take a look at the function f of x, let me just say log of 1 plus x. All right. So the graph will look like this. I'm going to shift 1 unit. Right, the original logarithm function, I'm going to shift it left 1 unit. All right, so here's the asymptote. Maybe it'll look like something like this. Of course, it'll pass the origin, right, since it's shifted this way. So that is actually the very definition of the Riemann sum. Right? If we divide this 0-1 interval into n equal parts, then we're taking, because the width of each small interval is exactly 1 over n, right? And the function is evaluated at the right edge of each small interval. Right? That's why we have 1 over n, 2 over n, that's the right edge. Right? So I'm using, so the limit as n approaches infinity of this is an, right? The limit of an is equal to the definite integral from 0 to 1 of that function, log of 1 plus x dx. Right? Of course, I'm going to let u equal to log 1 plus x. Right? Therefore, dv is just dx. Right? That way I can say du is equal to 1 over 1 plus dx. 1 plus dx. V is just simply x. And this integral is easily just uv x times log of 1 plus x from 0 to 1 minus 0 to 1 v du dx. Right? And so 1 goes into x, so I have 1 times log of 2. Log 0 goes to x, I have log 1. Log 1 is just 0. So I have exactly just log 2. Log 2 for this part, minus 0 to 1. I have x plus 1 minus 1 of 1 plus x dx. That is log 2 minus integral from 0 to 1. 1 minus 1 over 1 plus x dx. Right? And that is equal to log 2 minus, the antiderivative is x. Right, here's x. Antiderivative of this is just log of 1 plus x, right? So altogether evaluated from 0 to 1. I have log 2 minus, in the bracket I have 1 minus log 2. I have 0 minus log 1, still 0. I have twice of log 2 minus 1. That's log 2 to the power of 2, 4 minus log e. That is log 4 over e. Right. And since I already took logarithm, right, logarithm approaching this, so the original limit, right, is approaching 4 over e. And of course there is a second method. It's called Stirling formula. Stirling. Just as straightforward. So n factorial. When n gets very large, we can have its approximation. So it's approximately n over e, quantity to the power n times square root of 2 pi n. Right? Meaning this over that, take the limit, approaches 1. Right? We can just replace n factorial under multiplication or division, right, when taking the limit. Right? So that way we can rewrite our, let me just denote it as an. So that way, an, in fact, I'm going to multiply everything together, right? First of all, common denominators. So n plus 1, n plus 2, and so on and so forth. Right, n plus 1, n plus 2, all the way, n plus n. Right, all together, raised to the power 1 over n. Right. Still, I'm going to multiply everything together. Right, so down here I have n many n multiplied together. N to the power n. Up here I have so 1 plus 1, n plus 1 times all the way down, all the way up to 2n. That is 2n factorial over n factorial. All right, that's the result of doing this division. Just because the remaining n factorial will be cancelled out because only up to n plus 1, right? So 2n all the way down to n plus 1. So then I can just raise to the power 1 over n. Right? Then I can just replace n factorial with just this quantity and also 2n factorial. So 2n factorial is asymptotically equivalent to just replace n with 2n. 2n over e to the power also 2n times square root of 4 pi n. Right? So therefore this should be equal to this divided by that. Right? First of all, I'm going to write down this divided by that, n divided by this. So let me just write everything down. So 2n to the power of 2n, 2n to the power of 2n, 2 to the power of 2n times n to the power of 2n, right? Over e to the power of 2n times square root of 4 pi n, right, then divided by this, multiplied by its reciprocal. Its reciprocal is what? E to the n and n to the n times square root of 2 pi n. Right. Also divided by n to the n. And altogether to the power of 1 over n. Right? Then what is that? So n times n to the power of n to the power of n. That's just n to the power of 2n. N to the power of 2n. They just cancel out. And also, square root of 2 pi n and square root of 4 pi n. Perhaps I'm only left with just square root of 2. Right? Square root of 2 up here. And e to the power of n, e to the power of 2n. So I'm only left with just e to the power of n. Right? What else? So this is good. So that is equal to e to the, I'm going to distribute this power onto the bottom, right? So the n and the 1 over n, they just cancel out. I have e on the top. Distribute this power to square root of 2. Right? Then distribute the power to 2 to the power of 2n. I just multiply them together, right? So 1 over n times 2n gives me 2. 2 to the power of 2, that's 4. Right? Then take the limit. We have the well-known limit. As long as a is bigger than 0, we have a limit n approaches infinity of a to the power of 1 over n is always 1. Right? So that's approaching 1. So meaning it's approaching 4 over e. Same answer.